in civil engineering, we are going to talk about error analysis. First, we want to talk about the sources of errors in a numerical algorithm. The first type of error we are going to talk about are round-off errors. All calculating devices perform finite precision arithmetic. That is, they cannot handle more than a specified number of digits. For instance, if a computer can handle numbers up to s digits only, where s is a number, then the product of two such numbers, which in reality have 2s or 2s minus 1 digits, for instance, if I have a number that has 2 digits, for instance 12, if I multiply it by another number which has 2 digits, for instance 12 again, I get a number with 144 digits, which has got 2 times 2 minus 1, that is 2s minus 1, that is 3 digits. For the computer, however, will only store it as an s digit number and use it in subsequent calculation using only the first 8 digits of that number. The effect of such rounding off may accumulate after extensive calculations. For instance, if we are doing a series of products, every time we do a product, we instead of storing 2s digits, if each number has s digits, instead of storing 2s digits, we are storing s digits. So, each time we are losing a certain accuracy. So, each time we are introducing inaccuracy, and as these inaccuracies pile up, these may become significant. In an unstable algorithm, as we have seen before in our first lecture, this accumulation of this round off errors lead to useless and or grossly inaccurate results. So, first type of errors we talked about was round off errors. The second type of error we are going to talk about are known as truncation errors. Truncation errors occur when a limiting process is truncated before it has reached its limiting value. A typical example of this may be a series which suppose converges after n terms, but suppose we truncate it, that is, we cut it off after the first n by 2 terms. So, if the series converges after n equal to suppose 10 terms, suppose we cut it off after we compute only 5 terms in the series, that is n by 2 terms. In that case, the last n by 2 terms represent the truncation error. The last 5 terms in the series where n is equal to 10 are not being accounted for. So, they represent the truncation error. For instance, whenever a nonlinear function is linearized, we get a truncation error whose magnitude is typically governed by the magnitude of the largest nonlinear term, typically the quadratic term. When we linearize a function, we ignore all terms which are higher than linear, higher than first order term. And if the first nonlinear term is the quadratic term, then the error has also dimension are also second order. For instance, here if we are considering a nonlinear function of x, f of x, which is linearized about the value x0, we can write f of x is equal to f of x0 plus the derivative of x f with respect to x evaluated at x0 times x minus x0, which is the linear term, plus the quadratic terms which represent the truncation error. Examples. Next we will consider examples of round off and truncation errors. We have already seen examples of round off errors when we try to integrate numerically yn equal to xn by x plus 5 over the interval 0 to 1. when we tried to evaluate this integral for various values of n using the following recursion formula, yn plus 5 yn minus 1 is equal to y 1 by n in our first lecture, we found that the inherent instability of this numerical algorithm led to accumulation of the round off errors, and very quickly, maybe even after just 5 iterations, we were getting results which had no relationship with the reality, that the results were totally wrong. We started with y0 equal to 0.182, and by the time we reached y4, we got a value of 0.165, which was totally different from the true solution. And this we found was because of the inherent instability of the numerical algorithm we used, which allowed these round off errors to pile up and lead to essentially meaningless results. In that case, round off errors led to meaningless results due to the instability of the algorithm. To see an example of truncation error, we consider numerical integration of the definite integral y of x integrated between the limits a and b. Suppose we use the secant approximation to evaluate this integral. We recall from our last lecture that the secant method consists of approximating the nonlinear function by straight lines connecting successive function values. That is, given the iterates xn and xn minus 1 as well as the function values f of xn and f of xn minus 1, we find the next iterate using the following update formula: xn plus 1 equal to xn minus f of xn times xn minus xn minus 1 divided by f of xn minus f of xn minus 1. Graphically, this means that this nonlinear curve in blue is approximated by straight lines joining points on the curve, which represent each iterate and its value and its function value. We further assume that in our iteration procedure using the secant algorithm, the step size we use is constant. That is, successive values of the independent variable x, for example xn and xn minus 1, differ by a constant step size h. Thus, the area between the curve y is equal to f of x and the x-axis is approximated with the sum I of h of the areas of a series of trapezoids, each with a constant base width of h. That is, this area between the curve and the x-axis is approximated by these trapezoids, each trapezoid representing an iteration in our secant update algorithm. So, each trapezoid has of course constant base h, since we are iterating with a constant step size, and since the total area under the curve is obtained by summing up the area of these trapezoids, we use the name trapezoidal rule for this integration scheme. Let us see what the trapezoidal rule means if we have 5 intervals for evaluating our function y is equal to f of x between these two limits. In that case, we can write I of h is equal to sum of the first trapezoid plus the sum of the second trapezoid plus the third and the fourth and the fifth trapezoid. And as you can see, the area of the base in each trapezoid is the same, the constant step size h, while the sum of the parallel sides is given by y0 plus y1. The truncation error, the error due to the approximation of the nonlinear variation of y with which is equal to f of x with a series of linear variations, in our case these trapezoids, is of the order of h square when h is small. Thus, what it means is that the error between I and I to h, where I is the exact value of the integral and I within brackets to h is the result of our trapezoidal integration scheme, where we have used a step size of 2h, is going to vary quadratically with respect to the step size. So, it is going to be very nearly proportional to 4h square, while if the step size is h, the error between the exact value I and the numerically evaluated value using the trapezoidal rule with a constant step size of h, I minus IH, is very nearly proportional to h square. Hence, if we take a ratio of the errors I minus I of h divided by I minus I of 2h, we see that this ratio goes as h square by 4h square, h square cancels out and we get a ratio of 1 over 4. Thus, we see that by reducing the step size by half, we are getting an error which is just 1/4 of the error with the step size with the previous step size. So, we reduce the step size from h to 2h and our error goes down by a factor of 4. We can see from this that we can achieve arbitrarily high accuracy by choosing the step size h to be sufficiently small. As we keep on reducing h, our error is going to become smaller and smaller, and the error is going to reduce quadratically with the step size h. However, reducing h means increased number of function evaluations and higher computational expense. This is because if our interval over which we are computing the integral remains the same, as we reduce the step size, we have more function evaluations. We have to evaluate the function at more points, and this leads to greater computational expense. In order to avoid having to take very small step sizes h, instead of using a linear approximation which we did here, one can try approximating y of x by a higher order polynomial. For instance, instead of approximating it y of x by a linear polynomial, we can use a higher order polynomial, for instance a quadratic function, quadratic polynomial. For instance, the area under the curve y of x may be evaluated by approximating yx with piecewise quadratic function. That would be an example of polynomial or P refinement, where we have approximated the function y of x by a higher order polynomial, now in this case a quadratic polynomial. Similarly, we can use cubic, quartic polynomials to approximate the function y over fx over our intervals, over our step sizes. Alternatively, if we continue with our secant, that is our piecewise linear approximation, while reducing the size of the step h, that would be an example of h refinement. These are very common ideas in numerical analysis: polynomial refinement and step size refinement or mesh size refinement. So, these are the two main types of refinements which people use to get more accurate solutions. However, instead of using either H or P refinement, there is an alternative and highly efficient method for reducing the truncation error. Its basic idea is due to Richardson, and it is known as Richardson extrapolation. In our particular problem, where we want to evaluate an integral within certain bounds, what it means is that if we evaluate the integral using the trapezoidal rule, if instead of reducing the step size h or increasing the order of our polynomial approximation, if we could persist with our linear approximation, that is we persist with the trapezoidal rule, but use the trapezoidal rule several times, that is for several values of h, and we combine the values of the integral obtained using these several values of h, we can drastically reduce the truncation error. Let us recall that the trapezoidal approximation to I is equal to integral of y of x evaluated within the bounds a to b has an error approximately proportional to the square of the step size h. Therefore, by evaluating the integral for two step sizes h and 2h and combining the results, we can come up with a vastly improved solution, as we will see in the next slide. Since the error is of the order of h square, we recall that I of h, which is this is the integral which is evaluated using the trapezoidal approximation with a step size h, differs from the true solution by h square. So, the error is can be written as k times h square, where k is a proportionality constant. Since the error is proportional to h square, we can write that the error is approximately equal to the proportionality constant k times h square. Similarly, if we reduce the step size, if we use a step size of 2h, then in that case the difference between I of 2h, where I is the error with a step size of 2h and I to h is the integral with a step size of 2h, and I is the exact value. The difference between these two values is given by k times 4 of h square. Subtracting these two, we see that 4 times I of h minus I is approximately equal to I of 2h minus I. 4 times I of h minus I, that is equal to 4 times k h square. I of 2h minus I is again equal to k times 4h square. So, these two are equal. So, this gives me an equation for the exact value of the integral, which is I. If we solve this equation for I, we get 3I is approximately equal to 4 times I of h, the integral evaluated with a step size of h, minus I of 2h, that is the integral evaluated with a step size of 2h. This leads me to the expression that the exact value of the integral is approximately equal to I of h plus 1/3 of I of h minus I of 2h. Thus, by adding the corrective term 1/3 I of h minus I of 2h to I of h, we get a much better approximation to I with far lesser error than I of h. That is, by adding this additional term, which is 1/3 times I of h minus I of 2h to I of h, we get an error, we get a solution, we get a value of the integral which is much closer to the true solution than I of h itself. Before entering into further details of error analysis, we would like to define a few terms which we will need in our discussion. First, terms that we want to define relate to two types of errors. If we denote A tilde to be an approximate value for a quantity whose exact value is A, then we define the absolute error in A is given by the approximate value minus to the true value. That is, the absolute error is A tilde minus A. The relative error, on the other hand, is given by A tilde is equal to A tilde minus A divided by A. This of course assumes that A is not equal to 0. If A is equal to 0, we cannot define the relative error. So, the absolute error is just the numerical solution A tilde minus the true solution A, while the relative error is the numerical solution A tilde minus the true solution A divided by the true solution A, assuming of course that the true solution is not equal to 0. A bound on the magnitude of the error is known as an error bound. Thus, a bound on the absolute error is a bound on A tilde minus A. It is a bound on the absolute value of A tilde minus A. A bound on the relative error, on the other hand, is a bound on the absolute value of A tilde minus A divided by A. The above error definitions hold in general for scalars as well as vectors and matrices. In our definition of absolute error and relative error, we looked at scalars. A is assumed to be a scalar, but we are now saying that A can as well be a vector or a matrix, provided we can calculate a value for the magnitude of the vector or the matrix, or we can calculate a value of the norm of the vector or the matrix. Once we can calculate the value of the magnitude or the norm of the vector or matrix, we can use that norm to define error bounds for the vector or the matrix. That was about errors, about relative errors and absolute errors. Next, how do we measure errors? How do we decide how much is the error? To decide that, we have to talk about the measures of accuracy. In order to talk about measures of accuracy, we want to talk about decimals, the errors in terms of decimals and errors in terms of digits. The number of digits in a numerical value does not include the zeros at the beginning of the number, as these zeros only help denote where the decimal point should be. However, if we are counting the number of decimals, one has to include the leading zeros to the right of the decimal point. This becomes clear if we consider an example. For instance, the number 0.00548 has only 3 digits because we ignored the 2 zeros which occur at the beginning of the number. However, it has got 5 decimals since the number of decimals include the leading zeros to the right of the decimal point. If the magnitude of the error, whether it be the absolute error or relative error, in the numerical result does not exceed half times 10 to the power minus t, then we say by definition that the numerical approximation A tilde has t correct decimals. That is, if the error is lesser than 0.5 times 10 to the power minus t, the error is said to have t correct decimals. Again, we consider an example. If the absolute magnitude of error does not exceed, say, half into 10 to the power minus 3 or 0.0005, then we are certain that the numerical approximation has 3 correct decimals. This is evident because the error is only appearing in the 4th decimal place and the magnitude of the error is less than 0.0005. So, the first 3 decimals in A tilde in the numerical approximation must be correct. So, the number has 3 correct decimals. Our numerical approximation has 3 correct decimals. The number of digits in A tilde which occupy positions where the unit is greater than or equal to half into 10 to the power minus t, of course, we ignore the zeros at the beginning of the number, are the number of significant digits of A tilde. Suppose we have a numerical solution 0.001234 and we know that the numerical solution has an error of magnitude 0.000004. We can see that 0.000004 is of course less than 0.000005, which is equal to half times 10 to the power minus 5. Thus, we can see that our error is in the 6th decimal place, because the error is in the 6th decimal place. So, we can see that we have 5 correct decimals, that is, here in this solution t is equal to 5 and the solution 0.001234 is correct to 5 decimals. The number of digits in 0.001234 which occupy positions where the unit is greater than or equal to half into 10 to the power minus 3 are the first 5 digits. This should actually be half into 10 to the power minus 5. I apologize for the typo, but the number of digits in 0.001234 which occupy positions where the unit is greater than or equal to half into 10 to the power minus 5 are the first 5 digits. However, out of the first 5 digits, the first 2 digits are 0. The first 2 digits are 0. Hence, the number of significant digits is 5 minus 2 is equal to 3. So, we have 3 significant digits in our numerical solution. We have seen previously that numerical solutions are severely affected by round off. However, the way we do the round off is critical and can affect the severity of the errors arising from round off. If one simply chops off all the decimals to the right of the 10th decimal place, then the round off errors have a tendency to accumulate. Suppose our solution, our number has s digits, but if we chop it off after the 10th decimal place, then all the numbers which follow the 10th decimal place get removed from our numerical solution. But if we do this chopping arbitrarily, if we do this round off arbitrarily, then we will see that these round off errors have a tendency to accumulate. This is because the errors consistently have a sign opposite to the true value. For instance, if the true solution A is known to be always positive, after round off by chopping, A tilde minus A is always going to be negative, because after chopping A tilde has to be less than A, because we have got rid of the additional digits which follow the 10th digit. So, A tilde has got to be less than A and A tilde minus A will always be negative. Thus, the error from one chopping operation has no chance of cancelling out the error from a subsequent chopping operation. Similarly, if the true solution A is known to be always negative, after round off by chopping, A tilde minus A is always going to be positive, because A tilde is going to be less negative than A. So, A tilde minus A is going to be always positive. So, the errors from repeated round off operations will keep accumulating. The accumulation of the round off errors, depending on the number of significant digits, may quickly render the numerical solution meaningless after a certain number of iterations. A numerical solution can be considered arbitrary or meaningless when the magnitude of the cumulative error approaches the true solution. Round off errors due to chopping after t decimals can lead to errors as large as 10 to the power minus t. This can be seen, for instance, if we consider the number 0.555999 up to infinity. Then if we chop this number after 3 decimals, that is we store only 0.555 in our computer, in that case the error has dimension, error is of magnitude 0.000999999 up to infinity, and the limiting value of the error we can see is 1 into 10 to the power minus 3. That is, round off errors due to chopping after 3 decimals can lead to errors as large as 10 to the power minus 3. Thus, chopping is seen to have severe problems. As an alternative to chopping, many computers perform what is known as rounding. The rules for rounding are as follows. There are 3 rules. The first rule says if the digit to the right of the 10th decimal place is less than half into 10 to the power minus t, then the 10th decimal place is left unchanged. For instance, if we are considering t equal to 3, if the digit to the right of the 3rd decimal place is less than 0.0005, that is half into 10 to the power minus 3, which is 0.0005, then the 3rd decimal place is going to be left unchanged. If the digit to the right of the 10th decimal place, on the other hand, is greater than half into 10 to the power minus t, then the 10th decimal place is raised by 1. For instance, in our example, if our number is 0.3254, then the first rule would apply. The first rule would tell me I have to approximate 0.3254 as 0.325, because the digit to the right of the 10th decimal place is less than 5 into 10 to the power minus 4. However, if my number is, for instance, 0.3256, then we are going to store 0.3256 as 0.326, because the number to the right of the 10th, in this case the 3rd decimal place, is 0.0006, which is greater than 0.0005, which is half into 10 to the power minus 3. Then because of that, we have raised our 10th decimal place, we have changed 0.325 to 0.326. If the digit to the right of the 10th decimal place is exactly equal to half into 10 to the power minus t, then the 10th decimal place is raised by 1 if it is odd and left unchanged if it is even. So, these are our 3 rules for rounding. We will see that these rules result in lower error magnitudes. For instance, let us consider rule 3. The rule 3 says that if the, let us go back and look at rule 3 again, which says that if the digit to the right of the 10th decimal place is exactly equal to half into 10 to the power minus t, then the 10th decimal place is raised by 1 if it is odd and left unchanged if it is even. Since the probability of the 10th decimal place being odd or even is equal, each probability being equal to half, if rule 3 is followed, the resulting error will be positive or negative equally often, because the possibility of the 10th decimal place being odd or even is equal. So, the resulting error we get is also going to be positive or negative equally often. The errors will thus tend to cancel off and not accumulate. If the above rules are followed, then the error due to rounding off lies in the interval minus half into 10 to the power minus t to half into 10 to the power minus t. This has to be compared with the fact that if we do chopping instead of using our round off algorithm which we just described, we can get errors as large as 10 to the power minus t. Instead of 10 to the power minus t, now our errors lie in the range minus half 10 to the power minus t to half 10 to the power minus t. The superiority of rounding over chopping is thus clearly established. In addition, rounding errors have a greater tendency to cancel each other out. We showed this explicitly in case of rounding rule 3. However, the combined effect of rules 1 and 2 also favor the cancellation of errors. This is because the probability of the t plus 1th decimal being greater than the tth decimal is equal to the probability of the t plus 1th decimal being less than the tth decimal. The errors arising from rules 1 and 2 therefore have opposite signs and therefore have a tendency to cancel each other out. However, irrespective of whether rounding or chopping is used, for a numerical algorithm with a large number of operations, round-off errors due to one computation are bound to propagate to subsequent computations. The errors in one computation are going to affect the results of the subsequent computation. This is known as propagation of errors or error propagation. The subject of error propagation is complex. However, it is possible to come up with relatively simple bounds on the error for basic operations such as addition, subtraction, multiplication and division. The idea being that if we can come up with simple bounds for the basic operations, and since all numerical methods are basically a combination of these simple operations of addition, subtraction, multiplication and division, if we know the errors due to each of these individual operations, we can come up with an error for the entire numerical algorithm. So, if we can again going back, if we can bound these errors for the simple operations, we can establish bounds for our final numerical solution in case we compute the error for each intermediate step. If we compute the error for each intermediate step and we keep adding, we keep track of those errors, if we do some bookkeeping and if we keep track of those errors, then we can get the final error in our numerical solution. Consider for instance x1 tilde and x2 tilde, which are approximate numerical solutions for x1 and x2. Suppose also that the magnitude of the error for x1 is epsilon 1 and the magnitude of the error in x2 is epsilon 2. This we know. We know that the magnitude of the error in x1 is epsilon 1 and the magnitude of the error in x2 is epsilon 2. Now, suppose knowing those two values, knowing the magnitudes of the error in x1 and x2, we can write x1 is equal to x1 plus minus epsilon 1 and x2 is equal to x2 tilde plus minus epsilon 2. That is, x1 can be as low as x1 tilde minus epsilon 1 and can be as high as x1 tilde plus epsilon 1. Similarly, x2 can be as low as x2 tilde minus epsilon 2 and can be as high as x2 tilde plus epsilon 2. Hence, the smallest possible value for x1 is equal to x1 tilde minus epsilon 1 and the largest possible value for x1 is equal to x1 tilde plus epsilon 1. Similarly, the smallest possible value for x2 is also x2 tilde minus epsilon 2, where epsilon 2, recall, is the error in x2, and the largest possible value for x2 is x2 tilde plus epsilon 2. Since x1 minus x2 cannot be greater than the largest value of x1 minus the smallest value of x2, the magnitude of x1 minus x2 cannot exceed the largest value of x1 minus the smallest value of x2, we can write x1 minus x2 is bounded on the right, that is bounded, has an upper bound x1 tilde plus epsilon tilde minus x2 tilde minus epsilon 2. This should not be epsilon 1 tilde, it is actually epsilon 1. So, x1 tilde plus epsilon 1 minus x2 tilde minus epsilon 2. Similarly, since x1 minus x2 cannot be less than the smallest value of x1 minus the largest value of x2, we can write x1 tilde minus epsilon 1 minus x2 tilde plus epsilon 2 must be lesser than or equal to x1 minus x2, or x1 minus x2 is bounded from below, bounded on the left by x1 tilde minus epsilon 1 minus x2 tilde plus epsilon 2, because x1 tilde minus epsilon 1 is the smallest value of x1, smallest possible value of x1, and x2 tilde plus epsilon 2 is the largest possible value of x2. Combining equations 1 and 2, combining this equation with this equation, we can get a bound on x1 minus x2, which gives me a lower bound as well as an upper bound, which tells me x1 minus x2 is bounded from below by x1 tilde minus x2 tilde minus epsilon 1 plus epsilon 2, while it is bounded from above by x1 tilde minus x2 tilde plus epsilon 1 plus epsilon 2. Using a similar argument, now instead of considering subtraction, which we considered previously, instead of considering x1 minus x2, if we try to get bounds for addition, that is, we try to get bounds on x1 plus x2, by using a very similar argument, we can show that x1 plus x2 is also bounded from above and below by x1 tilde plus x2 tilde minus epsilon 1 plus epsilon 2 from below, and x1 tilde plus x2 tilde plus epsilon 1 plus epsilon 2 from above. Combining bounds 3 and 4, we get norm of, that is the absolute value of x1 minus x2 minus x1 tilde minus x2 tilde must always be less than epsilon 1 plus epsilon 2, and x1, the bound on x1 plus x2 minus x1 tilde plus x2 tilde is always lesser than or equal to epsilon 1 plus epsilon 2. Thus, the error due to subtraction is bounded by epsilon 1 plus epsilon 2. Similarly, the error due to addition is also bounded by epsilon 1 plus epsilon 2. We can write down the above result in terms of the following theorem, which states that the bounds for the absolute error due to addition or subtraction of two real numbers, in our case x1 and x2, are given by the sum of the bounds for the absolute error in each number. The sum of the bounds on the absolute error in each number, which is epsilon 1, which is the absolute error in x1, and epsilon 2, which is the absolute error in x2. A similar bound can be obtained for multiplication or division of two real numbers, but in this case the bound involves relative rather than absolute error. Up till now we have been considering absolute errors in evaluating our bounds, but in order to obtain bounds for multiplication or division of two real numbers, we have to consider relative rather than absolute error. Again, recall from our definition of relative error R, due to the approximation of a real number x by x tilde, we can define the relative error as R is equal to x tilde minus x divided by x, or x tilde is equal to x times 1 plus R. Suppose x1 tilde and x2 tilde are approximate numerical solutions for x1 and x2, and R1 and R2 are the relative errors in x1 and x2. In that case, we can write the product x1 tilde times x2 tilde as x1 times 1 plus R1. Recall, x tilde is equal to x1 plus R, so x1 tilde is equal to x1 times 1 plus R1 times x2 tilde, which is x2 times 1 plus R2, which gathering terms we can write x1 times x2 times 1 plus R1 into 1 plus R2. Thus, the relative error in x1, x2 is given by, again from our definition, the relative error will be given by x1 tilde times x2 tilde minus x1 x2 divided by x1 x2. So, if we take x1 tilde x2 tilde, we subtract x1 x2 from it, we get x1 x2 times 1 plus R1 times 1 plus R2 minus x1 x2. Dividing the whole thing by x1 x2, we get 1 plus R1 times 1 plus R2 minus 1, which is equal to R1 plus R2 plus R1 R2. Suppose our relative errors in x1 and x2 are much smaller than 1. In that case, we can write R1 plus R2 plus R1 R2 to be approximately equal to R1 plus R2. Similarly, the relative error in the quotient can be evaluated. For instance, x1 tilde by x2 tilde, which is the quotient of x1 and x2 in terms of its numerical solution x1 tilde and x2 tilde, can be written as x1 times 1 plus R1 divided by x2 times 1 plus R2. The relative error in the quotient will then be equal to x1 tilde divided by x2 tilde minus x1 by x2 divided by x1 by x2, which if we perform that operation, we get 1 plus R1 divided by 1 plus R2 minus 1, which is approximately equal to R1 minus R2 divided by 1 plus R2, which is not approximately, which is actually exactly equal to R1 minus R2 divided by 1 plus R2, and which is approximately equal to R1 minus R2 if R2 is much less than 1. Thus, if rho 1 and rho 2 are bounds on the relative errors R1 and R2, then it is clear that rho 1 plus rho 2 is the best upper bound for both R1 plus R2 as well as R1 minus R2. If we want to find bounds on R1 plus R2, which is the relative error due to multiplication, and R1 minus R2, which is the relative error due to division, we know that the relative error due to R1 plus R2 is bounded by the sum of the errors in R1 and R2, row 1 and row 2. Thus, if row 1 and row 2 are bounds on R1 and R2, then row 1 plus row 2 is the best upper bound for both R1 plus R2 as well as R1 minus R2. From this we get the following theorem, which states that in multiplication and division of real numbers, the bounds of the relative errors in the operations are added to get a bound on the error due to the operation. Basically, it tells me that the bound of the error due to multiplication and division is bounded by the sum of the relative errors in x1 and x2. Error analysis enables the user to make crucial decisions that have important bearing on the accuracy and efficiency of the calculation. For instance, if the product x1 x2 is to be calculated and x1 is known up to 3 significant digits and the true value of x1 is of the order 1, and we have to decide to what degree of accuracy we need to calculate x2. We already know the value of x1 and we know that it is accurate up to 3 significant digits, and then we have to calculate the value of x2 in order to minimize the error in the product x1 x2. From error analysis, it is clear to us that it does not make a lot of sense to use numerical methods to calculate x2 to say 6 significant digits. Why is that? This is because we know that the relative error in x1 x2 may be as high as half into 10 to the power minus 3, because our error in x1 is because x1 is known only up to 3 significant digits. So, the error in x1 is bounded by half into 10 to the power minus 3, and since the error in the product is bounded by the sum of the errors in the operands themselves, in that case the error in x1 x2 can be as high as half into 10 to the power minus 3. This follows from the fact, as we mentioned, that the bound on the relative error in x1 x2 is given by the sum on the bounds on the relative errors in x1 and x2. So, there is no sense in calculating x2 to an accuracy greater than 3 significant digits. However, it does make a lot of sense to ensure that the relative error in the calculation of x2 is not in excess of half into 10 to the power minus 3. That is, the error in x2 should not be more than 3 significant digits, since that is going to worsen the relative error in the product. Since the computational cost involved in the numerical calculation of x2 tilde depends on the degree of accuracy with which we wish to calculate x2 tilde, thus using error analysis we can find out to what degree of accuracy we wish to calculate x2 tilde. This gives us important information which helps us improve the efficiency as well as the accuracy of our numerical analysis. So, at the end of this lecture, let us sum up. So, we have looked at different types of errors, and we have looked at absolute errors, we have looked at relative errors, we have looked at how bounds on those errors, we have found out how we can bound errors, absolute errors as well as relative errors, and we have shown how we can use those bounds to find out the total error estimate for our numerical solution. By bounding individual operations such as addition, multiplication, subtraction, and division, we can actually find bounds on the total numerical solution. Next time we are going to continue our discussion on error analysis and look at how if we know the errors on individual variables x1 through xn, and we can find out the error on y, which is a function of individual variables x1 through xn.